Okay, good day. I am Mr. McCully. This is Pre-Calculus, lesson number 3, domain range, one-to-one functions, and inverse functions. So let's get right to it. Today we're going to find the domain and range of functions. We are going to compose functions. We are going to find the inverse of a function, and we're going to determine when a function's domain must be limited to find an inverse. And that's something that we will use again and again this year simply because we're going to spend a lot of time in trig, but we'll get to that. So let's review domain and range rules. And for those of you who had Honors Algebra 2 last year with me, the rules for finding domain and range are exactly the same as they were, and they will be exactly the same when you get to calculus next year, and they will continue to be the same. And so we're just going to use this, and you probably, if you remember back, you will recall that we went over these. So if a function f from a set A to a set B is a relation that assigns each element x in the set A to exactly to one set y in the set B, the set A is the domain or set of inputs, and the set B contains the range or set of output. Now, when you'll notice that I have this highlighted or and underlined and in italics. So set B can have more elements in it, but that doesn't necessarily mean that that is the range, that B is the range. Okay, the range is the set of all of the elements that are the outputs, but set B could have more elements in it. To find the domain, we're going to start with all real numbers, and so most of the functions that you've dealt with up to now have domains of all real numbers. Some of them have limited domains. The first two rules here are rules that have to do with algebraic limitations of the domain. So any input value that causes a division by 0 must be removed from the domain, and any input that causes the even root of a negative number must also be removed from the domain. Those two are non-real or undefined solutions. And then this last one is more of an applied problem. It says any input that does not make sense in the context of a problem must be removed. As for instance, if the domain is number of TVs sold, you can't sell a negative TV, so negative numbers don't make sense in the context of that particular problem. Let's move on to a couple elementary examples, and I think this is my first elementary example. Notice, sorry about that. And so when you see me say an elementary example, this is a very, very simple example, probably simpler than you will see in the practice work. If you need me to do more examples in class, I'll be happy to use class time to do that. But these are very, very simple examples. And so let's just make up an easy one. Find the domain and range of, let's see here, so A, we'll do f of x equals x squared. We'll do B, f of x equals 1 over x, that should be an equals, and C, f of x equals square root x. Some simple examples. So find the domain and range of all of these. All right, so if I go to my y equals here, and this is my graphing calculator, and so we're just going to do x, and then we're going to hit squared, and we will hit the graph of that thing. And the reason I bring this up is because you can really use your graphing calculator to get 90% of the way there, and then once you have a guess using your graphing calculator, you can use those rules to justify your solution. So when I look at this problem and I say what is the domain of this function, the x values, those are our inputs. Those are the values that we are allowed to plug into this thing, and the only values that we would remove from every single x value would be values that cause divisions by 0 or the even roots of a negative number. So when I see this parabola, it looks like it's going to go up to the left forever and up to the right forever. So all of these x values seem to be used. So we start with all real numbers, and I don't see any that's going to be removed from that. And so my first thought is going to be that the domain of this function is going to be the set of all reals. Now, I look at this x squared function and go back to my rules. Maybe I'll go back to them. There we go. Any input that causes a division by 0 must be removed. Well, there's no divide bar here, and there's no variable expression in the denominator of a function. Okay, so we can do that. All right, so I look at that second rule. Any input that causes the even root of a negative number. Now, 2 is an even number, but it's an exponent, not a root. So I have just justified that all reals is, in fact, my domain. Now, what are the outputs of this thing? So what are my range values of this particular function? Well, if I go back to this graphing calculator, I notice that there are no negative values. The output values are usually what we're going to consider the y values. I see that there are no negative values here. So my guess is that the range is going to be everything greater than or equal to 0. And so I need to justify that based on the algebra. Well, we look back at this equation. I notice that it's x squared. And when you square a number, the result is always positive. So if I had like -4 times -4 is positive 16. There's no way I can get a negative number out of this. So I have to say, well, what's the smallest number? If all my negatives become positives, all my positives stay positives, can I get 0 out? Well, if I plug in 0, 0 squared is 0, so that's definitely a valid output. And so my range here is going to be all y values such that y is greater than or equal to 0. All right. That's how I'm going to write that particular one. And I could say, I could do a couple of different things, and we'll explore those as we move forward. All right, let's talk about f of x equals 1 over x. Now, we did this in the last lesson, and we saw that there was something funky going on in there, 1 divided by x, if you hit graph. You'll notice we have this thing here. Now, there looks like there's a little bit of a hole in this particular function. And it looks like there's no value for x at 0. And so I am going to say for my domain of this thing, let's see if I can do D instead of R, the domain is going to be all reals where x is not equal to 0. All right, so that's my guess, and I got to justify it using the rules. Okay, start with any input that causes division by 0 must be removed. Well, we said that 0, it must be out of there, and if I go 1 divided by 0, that makes sense. I can't have 1 divided by 0. That's undefined. So this all reals where x is not equal to 0, that seems to be a valid domain. I can plug in any other number, and I get a value out. All right, so my range is also going to be all reals where y is not equal to 0. And again, we can look at the graph if we want, and we can see that it looks like it gets real close to 0, but does it actually touch 0? Well, let's talk about these numbers here. For a fraction to be 0, the numerator has to be 0, but the numerator is always 1. It's not a variable expression. It just stays 1. So no matter how big x gets, either positive or negative, you're still going to have 1 divided by a very large number, either positive or negative. So even though it gets very close to 0, it's not actually equal to 0. All right, let's look at this last one, and so we can move on. So we're going to clear this out. We're going to hit second. We're going to hit the square root button. We're going to hit the x value, and we're going to take a look at the graph of this thing. All right, so we start with all real numbers, but we notice here there doesn't seem to be any negative values that have been graphed. Okay, well, that's a little bit different, but it looks like 0 is graphed and all the positive numbers are graphed. So by looking at the picture here, my domain, I'm going to say all values of x such that x is greater than or equal to 0. That's going to be my domain for this particular function, and at least my guess. Then I come over here. Well, I have a root symbol, and remember that the square root symbol is the same as the square. That's the same. Remember when we're talking about third, fourth, and fifth roots, we get something that looks like that. So sorry about that. I lost my place here for a second. Okay, so in the third root means that you have to multiply three values together to get the number under the root symbol. But this is an even root, and so when I go back to this rule here, any input that causes the even root of a negative number must be removed. And so any negative number that goes under the radicals bar would be an even root of a negative number. So clearly x has to be greater than or equal to 0. Well, what about the range? Well, I look at my range, and clearly if you can't plug a negative number in, you're not going to get a negative number out, because there aren't two numbers that you can multiply by themselves and the same number by itself and get a negative out. Positive times a positive is positive, and a negative times a negative is positive. So there's no y values here that are graphed. So I'm going to say that we have all of our y values such that y is also greater than or equal to 0. So those are some simple examples. All right, composition of functions. The composition of a function, f with the function g, is written as f with that raised dot g of x, and it can be simplified to f of g of x. And the domain of f of g is the set of all x's in the domain such that g of x is in the domain of f. All right, so let's talk about simple composition of functions. So let's get two simple ones. So let's go f of x equals x squared, and let's say g of x equals, let's say, x plus 2. And then we will say find f composed with g of x and g composed with f of x. Okay, so this thing can be rewritten as f of g of x. And so in the last lesson, we learned that f, let's say if I did f of 3, we would plug in 3 squared and we would get 9. Well, here we are plugging in g, and g is x plus 2. And so we're going to plug, just like we plugged the 3 into the x squared, we're going to plug the whole expression x plus 2 in. And if you remember from last year, one of my big pet peeves, don't be the guy that makes this x squared plus 4. When you have a binary expression that needs to be squared, you need to multiply x plus 2 times x plus 2. X times x is x squared, x times 2 is 2x, and then x times 2 is also 2x, so together I get a 4x, and then 2 times 2 is 4, so that's that composition. Now if we compose the other way, and this is important because most cases the direction in which you compose a function does in fact matter. Composition is not commutative like multiplication is. In multiplication, 2 times 5 is the same as 5 times 2. But we're going to see that f composed with g and g composed with f are not the same. So we rewrite this one such that g is on the outside of the composition of function and f is on the inside. And so we are going to plug in to g the function that is f, which would be x squared. And so since g of x is x plus 2, I'm just replacing x with x squared. So my final answer for this one is going to be x squared plus 2. And then we'll be done. All right, moving on. Inverse function. An inverse function is a function formed by interchanging the ordered pairs of a given function. That is the mechanics of it. The domain of the original function becomes the range of the inverse function, and the original function is if the original function is denoted by f, then the inverse is denoted by f inverse. That's how we're going to read this. It looks like to the -1 power, but we really read this as f inverse. To show that two functions, f and g, are inverses, we're going to compose g with f and compose f with g and show that both of the functions reduce to x. That is a example that we did last year. All right, so let's talk about a couple elementary examples. First, find the inverse of, let's do a simple one, f of x equals 2x plus 3. All right, So we defined back here that an inverse function we find by interchanging the ordered pairs. So the process for finding the inverse function is we're going to take it as y equals 2x plus 3, and we're going to switch x and y, and so I'll get x equals 2y plus 3, and then we're going to solve for y. So I'm just going to use use the symmetric property and flip these two over and say 2y plus 3 is equal to x, and then we're going to subtract 3, that'll give us 2y equals x minus 3, and then we're going to divide by 2, and we'll get y equals x minus 3 all over 2, or you could write it a half x minus 3 halves y equals, and so my final answer, f inverse of x, is going to be equal to x minus 3 all over 2, or this one, whatever you'd like. All right, so what's this one here? Yep, I got to do one more page before I can move on. So show that y equals 2x plus 1 and y equals, let's see here, x minus 1 all over 2 are inverses. And you know what, let's change this, and I apologize for doing this to you. Let's make this f of x and g of x. Show that these two are in fact inverses. And so to do that, we must compose f of g of x and g of f of x. And we can do that fairly quickly. So this is going to be f of, and we're going to replace this g of x with the actual function, which was x minus 1 all over 2. And then we're going to plug x minus 1 all over 2 in for x into the f function. So the f function is 2 times something plus 1, and that something in this particular case is x minus 1 all over 2. So x minus 1 all over 2. And notice that the 2's will cancel here. So that 2 and that 2 cancels. And I'll be left with x minus 1 plus 1. And then the negative 1 and the positive 1 cancel, so I'm left with just x. And then if I come over here, f of x is 2x plus 1. So this becomes g of 2x plus 1. And so g is defined as something minus 1 all over 2. That's what g is defined as. And that something in this case is the 2x plus 1. So I'm going to put my 2x plus 1 in there. And then we can get rid of the parentheses because there's nothing, there's no multiplications that I have to distribute or anything. So I've got 2x plus 1 minus 1 all over 2. And then clearly the plus 1 and the negative 1 cancel out. So I've got 2x over 2, and then the 2's cancel, so I'm left with x. All right, so we come over here to show that two functions, f and g, are inverses. Compose f with g and compose g with f, and both functions should reduce to x. And we showed in this last example, or this example here, that composition doesn't always give you the same value. So when you have, or when you're trying to show that two functions are inverses, again, it's rare that you get the same thing, and it's even rarer that you get x. Now, I picked these two specifically to show that they were inverses. And since they both reduce down to x, we can say that f and g are inverses. And we're done. Okay, so for a function to have an inverse, it must be 1 to 1. And so I'm going to start with an elementary, let's see, limit the domain. Okay, a function must be 1 to 1. So what does it mean for a function to be 1 to 1? Well, if I pull up a simple graph here, let's just pull up a simple Cartesian graph, and let's get rid of these numbers. We don't really need those things. For a function to be 1 to 1, first, for it to be a function, it has to pass a vertical line test. So if I grab a red vertical line, maybe, come on now, red vertical, there you go. Let's make this line a little bit less thick. We don't need to be that thick. Okay, so here's a vertical red line. That's good. So for a function, or for a relation to be a function, it has to pass this vertical line test, which means it can only pass the vertical line in one spot. For every one x value, there is only one y value. Now, for a function to be one-to-one, it must not only pass that vertical line test, but it also must pass a horizontal line test. So this particular function, if I move it to here, this particular function, it passed the vertical line test, that made it a function, but this is not a one-to-one function because it doesn't pass that horizontal line test. Clearly, we can see that there are 1, 2, 3 points where this particular function passes through the horizontal line. So this is a non-one-to-one function. All right, so what can we do about that? Well, sometimes what we can do is we can limit the domain. So here's an elementary example. Uh-oh, not responding. That's not good. There we go. Here's a simple example of where we can limit the domain. So if I say y equals x squared. All right, so y equals x squared. Let's throw a little graph in there again. And let's move this graph over. And let's come down here. And zoom back out. Let's let me grab my tool here and maybe pull this down. Okay. We know that y equals, go and give me my pen tool, there we go. Y equals x squared would have 0, 0 as a point, 1, 1 as a point, 2, 4 as a point, negative 1, 1, and negative 2, 4, negative 3, 9, and 3, 9. We have a graph that looks like this. All right. It doesn't take a whole lot of imagination to say that this is definitely a function. It would pass that vertical line test. And it also doesn't take a whole lot of imagination to see that it wouldn't pass a horizontal line test, because clearly, you know, negative 1 squared is positive 1 and 1 squared is 1, so we can easily have two x values with the same y value. And so here we have another 2x values with the same y value. And here we have, so this function can't be doesn't have an inverse as it's written. So let's put that down there. Y equals x squared does not have an inverse as written. W-R-I-T-T-E-N. I think there's 2 T's. You can correct me in the comments. As written. So what we can do is we can limit the domain to create a new one-to-one function. All right. So if I go back to the last thing we did, and let's say I bring this, there's my vertical line right there, or my horizontal line, and clearly it doesn't pass the horizontal line. Well, what if, and we're just saying that we're picking this, we get rid of that part. Now we have a function that passes the vertical line test and passes the horizontal line test. But how do we write it so that we're only talking about this portion and not the whole value? Well, we can rewrite by saying it is y equals x squared. We're going to put a little bit of put a semicolon there, and then we'll say x has to be greater than or equal to 0. So this thing limits So this portion right here limits the domain to positive real numbers and 0, and now we have a one-to-one function. And so this function could be found to have an inverse if we wanted to. And if we need to, I can do an example of that in class. Well, that's all I got for today, folks. So, our Star Wars fun fact of the day. In Empire Strikes Back and Return of the Jedi, Yoda, the latex foam puppet, has 4 toes, but when he was redesigned as a digital animation character for the Phantom Menace, he only has 3 toes. You'd think that they would get that particular fact correct. Well, that's all I got, folks. So you have a good day, and I will see you next time. Goodbye.